Hello and welcome to the Deep Dive. We are thrilled to have you with us today as we set out to answer a question that, well, it seems incredibly simple on the surface, right? But it actually breaks the mathematical frameworks of the smartest physicists on the planet. Today's mission is unpacking this deceptively straightforward question. Why is gravity so weak?
It genuinely is one of the most profound unsolved mysteries in modern physics.
Hmm.
We aren't just talking about a quirky piece of cosmic trivia here.
Right.
The weakness of gravity represents a fundamental gap in our understanding of the universe. It's this gaping hole in the standard model that physicists refer to as the hierarchy problem.
Exactly. And to get to the bottom of this for you, we've pulled together an expansive stack of sources. We're diving into advanced cutting-edge physics papers on M-theory and the Randall-Sundrum
Oh,
models.
those are fascinating.
Yeah, they really are. We're also looking at the absolute latest gravitational wave discoveries, parsing through some really lively debates from physics Reddit AMAs, and examining brand new research on quantum collapse and the world's first graviton detectors.
It is a lot of ground to cover.
It is, but the sheer paradox of this topic is what makes it so fascinating.
Yeah.
I mean, we walk around all day feeling like gravity is this massive, inescapable, overpowering force.
Of course we do. It holds us to the ground.
Right. There's a great piece from Novia in our sources that frames this perfectly. If you've ever tried to move an upright piano up a flight of stairs.
Oh, yeah, that is a nightmare.
Right.
Right.
Gravity feels incredibly strong in that moment. You feel it fighting you every single step. But structurally, universally, gravity is the absolute runt of the cosmic litter.
Okay, let's unpack this. We don't need to rehash high school physics, but we do need to establish the scale of the four fundamental forces just to understand the scope of the problem.
Yeah, the scale is really where the mathematical nightmare begins. As anyone following particle physics knows, everything in the physical universe is governed by the strong nuclear force, the electromagnetic force, the weak nuclear force, and gravity.
The big four. The big four, exactly. To quantify their relative strengths, physicists typically use the electromagnetic force as the baseline. So we assign electromagnetism a relative strength of 1.
Okay, so keeping electromagnetism at a baseline of 1, the strong nuclear force sits at about 100.
Right.
It's roughly 100 times stronger than the electromagnetic force, which completely makes sense given the immense energy required to bind the nucleus of an atom together.
Right, it has to be strong.
But going the other direction, the weak nuclear force sits at 10 to the power of -6,
Yeah.
or, 1/millionth the strength of electromagnetism.
And then we drop off a cliff to find gravity.
Massive cliff.
A ridiculously massive cliff. Gravity sits at 10 to the power of -38. That is a decimal point followed by 37 zeros and a 1. It is a staggeringly tiny number.
There was a fantastic analogy in one of the Reddit AMAs we sourced that, well, it just grounds this abstract number in everyday reality for me.
The fridge magnet one.
Yes, the fridge magnet. Think about a tiny, cheap 2-inch fridge magnet. You hold it over a paperclip, and the paperclip jumps up and sticks to the magnet.
Happens in an instant.
Right. In that split second, that tiny piece of magnetic material is effortlessly overpowering the gravitational pull of the entire Earth.
It really puts it in perspective.
It does. The collective mass of a planet weighing 6 septillion kilograms is pulling down on that paperclip, and a 2-inch promotional magnet from a local pizzeria easily beats it.
It highlights just how severely skewed the power dynamic is. And at the quantum level, these forces are transmitted by exchange particles.
Like tossing a frisbee back and forth, right?
Exactly like tossing a frisbee.
Yeah.
You have photons for electromagnetism, W and Z bosons for the weak force, and gluons for the strong force. But for gravity, the theoretical exchange particle is the graviton, though I should point out it remains unobserved.
Right. We haven't actually seen one yet, but there's another visceral example from the research that really sticks with you. Let's say you jump off a 10-story building.
Not recommended, but okay.
Not recommended. But if you do, gravity pulls you down. But it takes the entire mass of the Earth several seconds to accelerate you to the ground. When you hit the pavement, the thing that stops you isn't a macroscopic physical barrier. It's the electromagnetic repulsion between the electrons in the atoms of your shoes and the electrons in the pavement.
Yes, that microscopic electromagnetic force halts the momentum generated by an entire planet instantly.
Instantly. So what does this all mean for the physics community? I mean, the natural assumption might be that somebody just has to come in last place, gravity is just weak, and that's the end of it.
That'd be the easy way out.
Yeah, but the hierarchy problem dictates that the mathematical framework of the universe says gravity shouldn't be this weak.
No, it shouldn't. It all comes down to mass scales and the mechanics of the Higgs field. In the Standard Model, particles acquire mass by interacting with the Higgs field. The baseline energy of this field, its expectation value, sits at around 250 gigaelectron volts, or GeV.
To translate that for a moment, think of 250 GeV as the standard operating voltage for particles in our universe.
Operating voltage is a good way to put it. It's the energy scale where the weak and electromagnetic forces operate. But contrast that operating voltage with the Planck scale.
Here's where the math gets scary.
Very scary. The Planck mass is the energy scale where gravity theoretically becomes as strong as the other fundamental forces. That scale is 2.34 quintillion GeV,
Wow.
or 2.34 times 10 to the 18th power.
So we have 250 on one side and 2.34 quintillion on the other.
Yes.
This massive canyon between the two is exactly where the math breaks down. In quantum mechanics, virtual particles are constantly popping in and out of existence in the background of the universe, right? They're interacting with the Higgs field. And because of these interactions, the math dictates that quantum corrections should naturally drive the mass of the Higgs boson all the way up to the Planck scale. The equations desperately want to pull that 250 GeV baseline up into the quintillions.
If we connect this to the bigger picture, yet, it remains firmly at 250. For the mathematics of the Standard Model to actually work out, it requires an absurdly delicate cancellation of numbers, a phenomenon physicists call fine-tuning.
And the sources gave a great way to visualize the improbability of this fine-tuning.
The pencil analogy.
Yes. Imagine balancing a freshly sharpened pencil perfectly on its tip on a table. Now imagine a massive magnitude 8 earthquake hits that table, and the pencil just continues to stand there perfectly still.
Not falling over at all.
Exactly. That is the level of statistical improbability we're dealing with when looking at the mass of the Higgs boson. The math requires the quantum contributions to cancel each other out to an accuracy of 1 part in 10 to the 30th power.
Which tells the physics community that there is a massive missing piece to this puzzle. For decades, the favorite solution was supersymmetry, or SUY for short.
Right.
The theory proposed that every known particle has a hidden, much heavier superpartner. The mathematical existence of these superpartners perfectly cancels out the quantum corrections.
Effectively keeping that pencil naturally balanced despite the earthquake.
Exactly. The problem, as our sources heavily detail, is that the Large Hadron Collider has been smashing protons together at unprecedented energy levels for years now, and it hasn't found a single shred of evidence for these superpartners.
Nothing.
Nothing at all. The absence of supersymmetry at the LHC has forced theoretical physicists to seriously explore alternative frameworks.
Here's where it gets really interesting. This brings us to M theory and the concept of extra dimensions. Specifically, the brain world hypothesis.
This is wild stuff.
It is arguably one of the most elegant solutions to the weakness of gravity, even if it requires a significant leap in how we visualize reality. The Novier article in our stack offers the clearest analogy for this.
Let's hear it.
Imagine our entire three-dimensional universe. Every star, galaxy, and planet we can observe is just the two-dimensional surface of a wooden picnic table.
Okay, a picnic table.
Right. That surface is what physicists call a brane, short for membrane. In this framework, all the particles in the Standard Model, the photons, electrons, and quarks, are like ants. They are completely trapped on the surface of the picnic table.
Just crawling around on top?
Exactly. They can scurry forward, backward, left, and right, but they cannot dig into the wood itself, nor can they float in the air above it.
They are entirely confined to the brain. But the graviton, the theoretical particle carrying the gravitational force, operates under very different rules.
Gravitons are not ants. They're termites.
Termites, I love that.
They aren't trapped on the surface. They can actually bore down into the wood of the picnic table itself. That wood, representing a higher dimensional space that exists outside our observable universe, is known as the bulk.
This concept was formalized in 1999 with the Randall-Sundrum models, specifically RS1. Lisa Randall and Raman Sundrum proposed a framework utilizing a five-dimensional warped geometry.
5 dimensions.
Right. In their model, the universe consists of two branes separated by a microscopic fifth dimension. There is the Planck brane, where gravity originates and is incredibly strong, and then there is the TeV brane, or the weak brane, which is the physical universe we inhabit.
So the RS1 model suggests gravity originates on the Planck brane and essentially leaks across the bulk over to our universe.
To understand why it's so weak by the time it reaches us, you have to look at the geometry of that fifth dimension. As the graviton moves across the fifth dimension from the Planck brane to our TeV brane, gravity's probability function drops exponentially.
It gets weaker incredibly fast.
Exactly. To put it simply, imagine walking down a long, intensely warped hallway where every single step you take saps half of your remaining energy. Because this fifth dimension is exponentially warped, by the time the graviton reaches our universe, its physical influence has been immensely diluted.
It perfectly explains why gravity appears as a cosmic weakling. It isn't inherently weak. We are simply feeling the faint, distant echoes of a force at the very end of a higher dimensional tunnel.
It is a beautiful mathematical solution.
It really is. Now, with all these wild theories about extra dimensions and graviton termites, it is incredibly tempting to ask why we don't just throw out our current rulebook entirely.
People ask that all the time.
Right. If the math requires five-dimensional warp geometry to make sense, maybe Einstein's framework is just fundamentally flawed. But we can't throw it out because Einstein's general relativity stubbornly refuses to fail on the macro level.
It really does.
It keeps passing every single real-world test we design, even in the most extreme environments in the universe.
The recent observation from the LIGO, Virgo, and K-ADRA collaborations is a perfect example of this. They detected a gravitational wave event designated GW250112, which produced the clearest gravitational wave signal ever recorded.
And the way the physicists analyze that signal is a masterclass in modern astronomy. They utilize a technique called black hole spectroscopy. When two black holes merge, the resulting single black hole doesn't just settle into a perfect sphere immediately.
No, it's highly turbulent.
Right. It wobbles and vibrates, ringing much like a struck bell. This phase is known as the ring down.
Just as a physical bell emits specific acoustic tones, a merging black hole emits specific gravitational wave tones. Because the GW250114 signal was exceptionally clear, researchers were able to measure two distinct tones simultaneously for the very first time.
Which is incredible.
It is. According to the mathematics of general relativity, if you measure one tone, you can definitively calculate the mass and spin of the black hole. If you measure a second tone, you can independently calculate the mass and spin again.
And if Einstein's theories are correct, both sets of calculations should match perfectly.
Exactly.
And they did. With unprecedented accuracy, general relativity held up flawlessly under the most extreme gravitational stress test conceivable.
This raises an important question. It creates a profound tension in modern physics. General relativity beautifully describes the macro universe, the planets, stars, and galaxies. But the moment you zoom into the quantum level to examine the world of subatomic particles, Einstein's equations completely break down.
They just stop working.
They yield infinities and mathematical paradoxes. To bridge this gap and formulate a true theory of everything, gravity must be quantized. We have to prove that gravity is carried by particles, just like the other three fundamental forces.
And the race to empirically prove the existence of the graviton is officially underway. The engineering involved here is staggering. According to our sources, the Stevens Institute of Technology is currently building the world's first graviton detector.
Which is a massive paradigm shift. For decades, physicists like Freeman Dyson argued that detecting a single graviton was practically impossible.
Because the background noise of the universe would always drown out a particle that weakly interacting, right?
Precisely. But new quantum technologies are pushing past those theoretical boundaries. We also reviewed the recent Gravity Research Foundation First Prize, which was awarded to Srinath Manekhan and Nobel laureate Frank Wilczek.
Right. Their proposal completely shifts the paradigm of detection. Instead of looking for classical waves in space-time, they suggested using resonant acoustic detectors to probe the microscopic quantum structures of gravitational radiation.
It is brilliant. The method involves utilizing massive supercooled cylinders to detect the minute quantum acoustic vibrations of a single graviton interacting with matter.
Literally listening for a single quantum particle of gravity.
Yes. If they can capture this interaction, it would be the first empirical proof of quantum gravity, fundamentally altering our understanding of the universe.
Real, rigorous science tackling the universe's most complex mysteries is thrilling. But naturally, wherever there is a dense scientific mystery, the internet is always ready to manufacture its own weirdness. We need to take a brief detour to address a viral rumor highlighted in our research. There is a widespread claim circulating online that the Earth will lose gravity for 7 seconds on August 12, 2026.
Yeah, analyzing the NASA data referenced in the sources makes it clear this is unequivocally false. Gravity is not an external switch that can be toggled on and off by planetary alignment.
It doesn't just unplug.
No, it is an intrinsic property of mass. The only physical way the Earth could lose its gravitational pull is if it spontaneously lost a massive portion of its physical material, its core, mantle, and crust. Under the current laws of physics, a 7-second anti-gravity window is a complete fiction.
So you can safely cross that off your 2026 calendar. But as we pivot away from internet fiction, we actually land on some real physics that is arguably much stranger. We're talking about the possibility that gravity is the reason reality itself exists in a solid state. What if gravity is responsible for the collapse of the quantum wave function?
This touches on one of the deepest philosophical and mathematical questions in quantum mechanics. We know that subatomic particles can exist in multiple states or locations simultaneously, a state known as superposition, until they are measured or interact with their environment.
And at that point, the wave function collapses into a single, definite reality.
Correct. The mechanics of why this collapse happens remain heavily debated. Some theoretical frameworks propose that the collapse isn't triggered by a conscious observer, but rather driven spontaneously by gravity.
The sources outline two leading theories for this mechanism, the DOC-Penrose model and the continuous spontaneous localization, or CSL, model. The math in these models suggests that quantum matter is constantly evolving within a randomly fluctuating gravitational field.
Yes, it is the instability of this microgravitational field that forces the quantum superposition to break down and collapse into a singular state.
If these models are correct, the implications for our understanding of reality are staggering. General relativity established a century ago that gravity and time are inextricably linked.
Space-time is one unified fabric.
Right. Stronger gravitational fields slow time down relative to an outside observer, while weaker fields speed it up. Therefore, if the background gravitational field of the universe is constantly randomly fluctuating to force quantum collapse, it means time itself must be fluctuating along with it.
It is a mind-bending concept.
Time itself is jittering.
Okay.
When reading through the research, the immediate question is scale. How much is time actually fluctuating? Are these microscopic jitters enough to noticeably alter the passage of time?
The researchers quantified this effect by calculating the disruption for an optimal, theoretically perfect clock running for a full calendar year. The resulting time uncertainty, the jitter, amounts to about 1/10 million trillion of a second.
That is an unbelievably small margin.
It is so microscopic that it doesn't affect the calibration of our most precise optical lattice atomic clocks, nor does it impact the timing of massive millisecond pulsars spinning in deep space. It has absolutely zero practical consequence for macroscopic timekeeping.
Philosophically.
Philosophically and mathematically, it is a massive revelation. It proves that if gravity is the engine of quantum collapse, the fundamental fabric of time is fuzzy. It is not a perfectly smooth, continuous river. It has a microscopic, pixelated vibration to it.
We've covered an immense amount of ground today. We started by looking at how a standard 2-inch fridge magnet effortlessly defeats the gravitational pull of an entire planet. That anomaly led us straight into the hierarchy problem, revealing that the mathematical framework of the universe is balanced as precariously as a pencil during an earthquake.
Quite the balancing act.
Exactly. To reconcile that math, we examined the Randall-Sundrum models, envisioning 5-dimensional picnic tables where graviton termites bore through the bulk, explaining why gravity is reduced to a faint echo by the time it reaches our universe. And finally, we explore the very real possibility that gravity's microscopic fluctuations are causing the fabric of time itself to jitter, forcing the quantum world to collapse into the concrete reality we navigate every day.
It forces a complete reevaluation of how we interact with the physical world.
I want you to remember this the next time you drop your keys on the pavement or the next time you jump up in the air. You aren't just interacting with a mundane everyday force. You are engaging with an ancient cosmic mystery. You are feeling a force that might literally be leaking into our reality from a higher unseen dimension. And if we take that brain world hypothesis to its absolute logical conclusion, it leaves us with one final thought to consider.
What's fascinating here is, well, if gravity is free to leak out of our universe and into the higher dimensional bulk, could the gravity from other universes be leaking into ours? We know that dark matter is an invisible mass holding our galaxies together. We can't see it, we can't touch it, but we can clearly measure its gravitational pull. Could the unexplained phenomenon of dark matter actually just be the gravitational ghost of a parallel universe sitting right next to us on the cosmic picnic table?
What an incredible thought to end on. Thank you for joining us on this deep dive. We hope you walk away looking at the world and the invisible forces holding it together a little bit differently. Keep questioning the universe, and we will see you next time.